Okay, I hope you've had a chance to look at some of this stuff really during the break here. But let's go back to that tri-state driver issue. Now what I want to address here is an application. So look, I'm looking really at a bus consideration, okay? So I'm looking at a bus consideration. Now imagine, okay, and I'll just consider one bit for example here, that I have a register. And let's say this register has an output which we'll call Q, all right? And maybe I'll call this, for example, register A. Reg A. And maybe over here, for example, I have another register, all right? It also has an output, let's say, called Q. And we'll be looking at this in more detail a little bit later on, okay? And let me call this register, for example, register B, all right? Now, we may want to communicate data between registers, and we may have a number of registers whereby we might want to put the contents of A into the contents of B, and so on and so on. Well, how do I connect, as it were, the outputs of these registers to, if you like, a common bus? How do I actually do that? Now, if I were to connect this output here directly to this bus, and this output here directly to the bus, we would have a problem, okay? Supposing this output, the contents of this register, it had a 1 sitting there. And let's supposing this register had a 0 sitting there for the Q value. Well, then I'd be trying to connect a 0 and a 1 together. And this would result actually in what we call bus contention. All right, so really you can only have the output of one register connected to the bus at one time. And the other outputs really have to be disconnected. All right, now we can do this by means of a tri-state driver. So in other words, I can take that tri-state driver, I'll take the output of the register, feed it into the tri-state driver, then I can take the output of the tri-state driver and connect it to the bus. And remember, we have an enable on here. I'll call this, if you like, enable B for this tri-state driver here. Similarly, we will take this register, we'll feed this into a tri-state driver. Okay, this tri-state driver can then connect to the bus, and I will call this my enable A. All right? Now, if this register is driving the bus, that's this one here, then this one has to be disconnected. Okay? Now remember, the enable serves the function of what? Of really connecting the input to the output. When this device is disabled, it looks like an open switch. Okay, and there is no connection from this input to this output. In other words, you could perhaps model it like this, like a little open switch. So when this is disabled, this is an open switch. And so this is one application that we use these tri-state drivers, is for us to connect, as it were, multiple registers to a single bus. All right? Well, let's now move into a Boolean algebra consideration, and we'll look now at some Boolean identities. So Boolean algebra, okay? First of all, let's look at what we'll call the OR relations, okay? So these are the OR relations, all right? Let's write these down. So really, comes from our OR function here, where I have, let's say, two inputs, A and B. Call this output whatever you want. Let's call it X. All right, and we'll say X is what? A or B. All right, what are these OR identities, if you like? All right, now you can prove these identities, and I'll get you to do this yourself, really by looking at what? By looking at the truth tables. Okay, so all of this stuff that we're going to go through can be proved by consideration of a truth table. So our OR relations. If we have A or 0, what is the result? A or 0 must give me what? Whatever A is. Okay? If I have A or 1, doesn't matter what A is, basically the result is 1. If I have A or A, well, the result there is simply what? A. And of course the other relationship, if I have A or B, well, that's really the same as B or A. So those are my OR relations. Let's look at some AND relations. Okay, AND relations. So what we're going to end up with really are a list of Boolean identities. Really not that many that we consider. So AND relations. Okay, once again, let's just draw the little gate function there. So here we have our gate. This is A, this is B, and the output, let's call it X. X is what? A, B. All right, so let's look at this. A ANDed with 0 simply gives me what? 0. Okay, doesn't matter what A is. A ANDed with 1 would be equal to whatever A is. A ANDed with A is going to be whatever A is, A. And of course, AB is the same as BA. So what we have there really are 8 identities, 4 from the OR relations and 4 from the AND relations. Okay. All right, let's look at involution. Some of these things are very obvious. This is the involution theorem, okay? Involution. What is that stating? That's stating that A bar bar is really what? It's the same as A, an obvious one, okay? Let's look at what we call complementation, the complementation theorem. Okay, what is that stating? Complementation theorem is simply stating that A or A bar is equal to 1. Once again, you can prove that from a truth table there. Okay, it's very obvious. If A is 1, what's A bar? 0. Okay? If A is 0, what's A bar? 1. Okay? So you've got what? Either 1 or 0 is 1, yes, or 0 or 1 is 1. Okay? Then what else do we have? We have A ANDed with A bar. That's 1. If A is a 1, let's say, A bar is a 0. So this must be a 0. If A is a 0, A bar is a 1, still must be a 0. Okay? That's called complementation. All right, let's look at another theorem. This is called absorption. Absorption. Okay? What is this stating? This is really stating that A or AB is really equal to A. Look, you could sort of prove this in the following way, like factoring. It's a little bit like factoring, okay? You can factor out the A. What are you left with? A into 1 or B, all right? 1 or anything is going to be what? 1 or anything. Doesn't matter what B is. 1 or anything is simply going to be 1, isn't it? Simply going to be 1. And so that is equal to A, all right? All right, now let's look at consensus. And this is a very powerful theorem. Okay, the consensus theorem, all right? Now, supposing I have a function f that is equal to, let us say, A or A bar B. Once again, I'm not going to prove this. I'd like you to go away and prove this really using a truth table approach, okay? Basically, the consensus theorem states the following. If I have a variable in one product term, and then that same variable in its complemented form in another product term, then I can form what is called an optional product term. Okay, so I have A in this term, and I have A bar in this product term here. And so basically I can take the consensus of these two and perform or form what we call an optional product term. And that optional product term would be what we have left, as it were, over here. I've got A and A bar. The optional product term is simply B. So I could rewrite that function now, and I could rewrite it as f is equal to A or A bar B. All right, those are the two original terms. These are often called the parent products. That's one parent product. That's another parent product there. This guy is the optional product. It's optional, so I can simply add it to the Boolean equation. It doesn't change the value of that Boolean equation, and so I'll just add it. Now, the only reason for adding the optional product term is if it's going to help in the minimization process. If it doesn't help reduce the complexity of the original equation, well, I don't do it, okay? Now, does it help in this case? Here is the optional product term added to the original Boolean equation. Does it help? Well, look, really B is going to what? Absorb this term here. We could do this, let me just expand this out. So we've got what? A or, okay, it's as if what? I can sort of factor out the b. So let's put the b into what? A bar or 1. Okay, now 1 or anything is what? Is 1. And so this function then simply becomes a or b. All right, so I've reduced the complexity of this function, resulting in a or b, using this consensus theorem. Okay? Look, let's just take another example here. We won't actually minimize this one. We'll take an example where we do minimize in just a moment. But look, let's look at this function. F is equal to, let's say, a, b bar, let's say c, all right, or b, d, e, all right? Let's look at that. That's some function that we have, all right? Now, I look at this. This is a parent product term. This is a parent product term. I've got b complemented in this term and b in this term over here, okay? So I can form the consensus between these two product terms. Here's b bar and here's b. So the optional product, as it were, is what I've got left. It's the AC. So let's write that down. AC DE. So that is my optional product. AC DE. Okay? So I could rewrite my expression now, my function, as being A B bar C or B D E. Those are the two original terms called the parent products, plus the optional product term, which is A C D E. As I say, that's the optional term sitting there. All right? Now, you may not use this. It may not help in that minimization process. If it doesn't, just leave it off. But sometimes forming an optional product can actually help in that minimization process. Okay? So let's just go ahead and look at an example using this consensus theorem. Okay, here is an example, and we'll see if this consensus theorem here is going to help minimize that Boolean equation. Okay, we'll see if it can help minimize that Boolean equation. All right, so what we'll do first of all is we'll look at this term here and this term here. We've got A and we've got A bar, so I can basically form the consensus between these two parent product terms, and the optional product in this case is just B. That's the optional product. Okay, so I can rewrite that whole function now. So let's go ahead and do that. So F is equal to, let's rewrite that whole function. What is it? A or A bar B or BC, this term, or A bar B bar D, all right, that's the original function, and I'll add to it this optional product, which is B. Okay, now does this help at all? Well, look, this B here could absorb this product term here, and it could absorb this product term right here, and that's certainly going to reduce the complexity. So let's see if we can rewrite that, okay, and see what it looks like. So this is equal to, isn't it? I've got my first term, which is A, okay. Let us, as it were, factor out the B, there it is, the B, into what? 1, or, what have I got here? This is what? A bar, yes, and this term over here, or C, close the bracket. All right, now you could expand that out, couldn't you? If I expand that out, I get each one of those terms. Okay, and then I've got my last term here. Better include this guy in, which is, what is this term right here? That's A bar, B bar, D. Okay, there's my last term sitting there. Well, 1 or anything, okay, 1 or anything is what? This whole thing would just be 1. So I can now rewrite that function as being what? That's just 1, so I've got A or what? B or this last term here, which is what? A bar, B bar, D. Okay? All right, so I've reduced the complexity quite a bit so far, okay, compared to the original. Now, what else can I do? Can I use consensus again? Well, yeah, you can. I could take the consensus between, let's say, A, and once again, A bar over here. What am I left with if I take that consensus there? Well, I'm just, the optional product term is what? It's just B bar D, isn't it? So the optional product term is B bar D. So I could what? Rewrite the function now and add the optional product to it. So if I do that, that's A or B. All right, that's that and that. Or this term, which is what? A bar, B bar, D. And I can add to it the optional product term, which is what? B bar D. Okay, there's the optional product term added to it. Well, look at this. B bar D is also contained in this product term here. So really this product term is going to absorb this product term. Okay, and so I can take that a little bit further and I can say it's A or B or B bar D into what? The A bar or 1. 1 or anything is 1. And so this simply comes out to be A or B or what? B bar D. Okay? That's what that comes out to be. Well, can you go any further? Well, let's look. Well, I've got a B bar in this product term and a B in this. So yep, sure, I could take an optional product there. What would the optional product be? What are you left with over here? Okay, it's just D. So the optional product is D. Okay, so I could rewrite my function now. My function then is what? Is A or B or, let's say, B bar D or what? D. Well, this D, is it not, is going to absorb this D B bar. Okay, so I could show that that's equal to what? A or B or, if you like, factoring out the D, what am I left with? I'm left with B bar or 1. Once again, 1 or anything is just 1, and so the function then is A or B or D. Okay, so consensus then allowed me to take something that's fairly complicated, fairly involved, and minimize it to what we have here, A or B or D. Okay, so consensus is actually a very powerful theorem. Okay? Okay, the last thing I want to talk about in this section, in this part 2, are really De Morgan's laws. Okay, and we're looking really 2 laws. Number 1, okay, if I have A, B, C, a bar over the whole thing, that is equal to A bar or B bar or C bar. Okay, number 2, if I have A or B or C, bar over the whole thing, that is equal to A bar, B bar, C bar. Okay. Now, how would you prove those relationships? Okay. We're not going to do it here, but how would you prove it? Yes, you'd use a truth table as one approach to proving this relationship. Okay. All right, now look, there are not that many relationships to remember, but you do need to remember these. It's important that you do this. So let's take another break at this point. Go back through this material and make sure you understand what we've done. And in the cases that you want to here, go ahead and prove these identities using a truth table.